So for question 6, we're going to find the equation of a normal plane and osculating plane of this position vector, cosine t, sine t, and ln of cosine t at a point 1, 0, 0. So first things we want to do is we want to find some sort of t value that'll satisfy this point. So if we're looking at this point, 1, 0, 0, we want to find out what t value could we plug in that would give us these points. So we see that if we plug in t equals 0, cosine of 0 is 1, sine of 0 is 0, and ln of cosine of 0 is also 0. So then we get 1, 0, 0. So we see that t of t, our unit tangent vector, will give us r prime of t over the magnitude of r prime of t. And our normal vector will give us t prime of t over magnitude t prime of t. And our binormal vector will give us t of t cross n of t. So we're going to need all those. So first we need r prime of t. So to do that, take the derivative of r of t. So derivative of cosine would be negative sine. Derivative of sine t would be cosine t. And derivative of ln cosine t will give us 1 over cosine t times a negative sine t. So I can rewrite that as negative sine t over cosine t. And that is our r prime of t. So now we're going to get the magnitude. To get the magnitude, we'll take the square root and square each component and add them together. So negative sine t squared would just be sine squared t. Cosine t squared would be just cosine squared t. And negative sine t over cosine t, well, that's the same thing as saying negative tan. So, but it's going to be squared. So we see that sine squared t plus cosine squared t, that's our Pythagorean identity. That's just equal to 1. So inside we have 1 plus tan squared, which is equal to secant squared t, which is also just equal to secant t. Since it's under the radical. So our t of t is r prime of t over the magnitude of r prime of t. So we can write this as sine t cosine t, and I'll keep it as negative sine t over cosine t. And then we would divide by secant t, but we know that 1 over secant t is the same thing as saying cosine t. So we can bring that on the outside instead of dividing. So multiplying that cosine t across, we would get negative sine t cosine t. Cosine t times cosine t is cosine t squared. And then the cosine t's would cancel, leaving us with sine t. So from here, our first component, we have a negative sine t cosine t. We know from the double angle theorem that sine of 2t would be equal to 2 sine t cosine t. So if we divide by 2, we get sine 2 be sine t cosine t, but it's negative, so we could just multiply by negative 1 on both sides. So then we can replace that with a negative sine 2t over 2, and we can just keep these the same. And now we have t of t, but we're going to need our normal. So to get normal, we need t prime of t over the magnitude of t prime of t. So we can start by taking the derivative. So derivative of negative sine 2t over 2, we could do that on the side here. That's the same thing as saying negative 1/2 sine 2t. So using the product rule, we'll have negative 1/2 times the derivative of the second, which is cosine u, or cosine 2t times 2. And we see that the 2's cancel, 2 and 1/2, leaving us with negative cosine 2t. So that's what we'll put here, negative cosine 2t. Derivative of cosine squared, we can also do the product rule there. 1 times the derivative of second, which would be negative sine t cosine t. And then we're going to add that again, so we'll just get a negative 2 sine t cosine t. Negative 2 sine t cosine t. And let me move this. Derivative of a negative sine would be a negative cosine t. And that is our t prime of t. So we're also going to need the magnitude. But we know our t value, we found right here, t equals 0. So what we can actually do is find t prime at 0. And if we did that, negative cosine of 2 times 0, negative cosine is 0, would just be negative 1. Negative 2 sine 0 cosine 0, that would be 0. And negative cosine 0 would also be negative 1. So now that's t prime of 0, but we're also going to need the magnitude of t prime of 0. So we can do that by taking negative 1 squared, so that's 1 squared plus 0 squared plus 1 squared, which equals root 2. So now our normal vector, or n of t, would be 1 over root 2, negative 1, 0, negative 1. Okay, so now we have n of t. We can, this is actually n of 0, not n of t. So now we can, now that we know n of 0, we can actually find t of 0, which is right here. We could have done that before, but we can do that now. If we plugged in 0 for that, we would get 0, 1, and 0. Now we have n of 0 and t of 0, so we know that our binormal vector, this time at 0, b of 0 would be equal to t of 0 cross n of 0. So we're going to cross here and here. So if we did that, b of 0, we got I, j, k. T's first, so negative 1, 0, negative 1. Oh, I'm sorry, it's the other way around. T is 0, 1, 0. And then we're crossing with n, negative 1, 0, negative 1. And there's a constant here, 1/2, 1 over square root of 2, but that's not going to matter, no. We'll see why in a second. If I pull out an I hat, we get 1, 0, 0, negative 1, minus j hat, 0, 0, negative 1, negative 1, plus k hat, 0, 1, negative 1, 0. Now we can do our cross. 1 times negative 1 is negative 1, 0, subtract them, we get negative 1. 0 times negative 1 is 0, same thing. We get nothing in the j. And then we get 0 and then a negative 1, but we're subtracting them. So we get a positive 1 here. So our b of 0 would be negative I hat plus k hat. And then we still had this constant over here, which is just over root 2. So this is our binormal vector. So if we want to rewrite this binormal vector, we can write it as like this: 1 over root 2, negative 1, 0, and a positive 1. So we're not going to really need this 1 over root 2. We can discard it. So we're just going to focus on this part, negative 1, 0, and 1. And that's going to help us find our osculating plane. But we're also going to need our normal plane. And to do that, we have that with t of 0. We're using the tangent to find the normal plane. So we're just going to do a reminder that t of 0 is 0, 1, 0. So these two vectors are going to be important. So now let's go find the equation of the osculating plane first. So for osculating, we know that the general formula of an equation of a plane would be r minus r naught dotted with an n vector is equal to 0, where n is a normal vector to the plane and r naught is a point on the plane. So for this n vector here, we're going to use what we found right here, this vector. And r naught is going to be the point that we started with. Should be 1, 0, 0. Again, that is our point. And r will be a general point, x, y, z, or general vector. So writing that, we'll have x comma y comma z minus 1, 0, 0. And that's all going to be dotted with our b of 0, which is negative 1, 0, and 1. Should be all equal to 0. So we can rewrite this as x minus 1, and then y and z, dotted with negative 1, 0, 1, equal to 0. So now we're doing the dot product. So this will give us negative x plus 1. There's no y, and we're getting a positive z, and that's equal to 0. So we can subtract negative 1, negative 1. We get negative x plus z equals negative 1. If we wanted that negative 1 to be positive, we can multiply by negative 1 on both sides, leaving us with x minus z equals positive 1. And that would be our equation of the osculating plane. Now for the normal, we're going to use the same equation, r minus r naught, dotted with an n vector, equals 0. But this time our n vector will be this t of 0, 0, 1, 0. So if we did that, we'll get the same x minus 1, y, z. But we're going to dot it with, we said 0, 1, 0. It's equal to 0. So there's going to be no x. There's going to be a y dotted 1. So that's just a y. There's no z, and that's equal to 0. So we get y equals 0. And that will be the equation of our normal plane.